China is investing billions in quantum radar to expose America's stealth fighters. But what if a US fighter changes the radar return instead of hiding from it? A plasma sheath could disrupt detection, break missile tracking, and leave sensors chasing ghosts. The fighter is there. The radar cannot prove it. Traditional radar sends out electromagnetic energy and waits for the reflection. The signal travels toward the aircraft, hits the airframe, and returns to the receiver. At a distance of 400 kilometers, that round trip takes approximately 2.67 milliseconds. That sounds instant, but the returning signal is incredibly weak. The radar must separate it from atmospheric noise, ground reflections, electronic interference, deliberate jamming, and every other object inside the beam. Stealth aircraft make the problem harder by reducing the amount of energy reflected back. Quantum radar attempts to improve the comparison process. The system creates two related signals. One travels toward the target, the other stays inside the radar as a reference. When the return signal comes back, the system compares it with that stored reference. It is not necessarily looking for a bright, obvious echo. It is looking for a statistical relationship hidden inside the noise. Under carefully controlled conditions, quantum illumination research discusses an advantage of approximately 6 decibels in reducing detection errors. But that does not mean 6 times more range. It does not mean quantum radar sees through every stealth coating. It means the radar may have a better chance of identifying a weak target under specific conditions. Atmospheric loss, receiver sensitivity, signal processing, and distance still matter. The useful correlation can weaken after the signal travels hundreds of kilometers through the atmosphere. Most importantly, quantum radar still depends on the target producing a usable electromagnetic return. If the target changes that return before the receiver can interpret it, the advantage may be reduced. That is where plasma enters the story. Modern stealth is not a magic cloak. It is signature management. The aircraft uses its shape to redirect radar energy away from the transmitter. Special materials absorb part of the signal. Engine inlets are hidden and carefully shaped. Weapons are carried internally. Sharp edges are aligned. Radio emissions are controlled. The goal is not to produce zero reflection. The goal is to make detection happen later, classification take longer, and targeting become more difficult. In the basic radar equation, detection range is related to the fourth root of radar cross-section. That means a 100-fold reduction in radar cross-section does not produce a 100-fold reduction in detection range. It produces approximately a 3.2-fold reduction. A 10,000-fold reduction produces roughly a 10-fold reduction in theoretical detection range. That is still a massive tactical difference. A radar that could detect a conventional aircraft at 400 kilometers might detect a much quieter target at a dramatically shorter distance, depending on radar power, frequency, geometry, and atmospheric conditions. But stealth is never uniform. One radar band may struggle while another detects a rough contact. An infrared sensor may see heat. A passive receiver may detect emissions. Conventional stealth controls the aircraft's surface. Plasma stealth attempts to control the space around the aircraft. That is not a better coating. That is a completely different engineering problem. The effect of a plasma layer depends on one critical factor, its density. Every plasma layer interacts with electromagnetic energy at a certain frequency. If the plasma is dense enough, it can absorb, reflect, or distort radar waves operating in that range. Radar waves come in different sizes. Some radars use longer waves, around 10 centimeters. Others use shorter waves, closer to 3 centimeters. A plasma layer that disrupts one type of radar may have little effect against another. Longer waves are generally easier to interfere with. Shorter waves require a denser, more energetic plasma layer. The fighter would therefore need to adjust the plasma in real time, matching the radar threat as that threat changes. A plasma sheath naturally forms around spacecraft returning from orbit at extreme speeds. But a fighter traveling at Mach 2 does not automatically generate the same intense layer. To create one, the aircraft would need an active system capable of producing and shaping the plasma around the airframe. The layer would also change with altitude, speed, temperature, air density, and radar frequency. The radar might still see a brief return, but the signal could become weak, distorted, or impossible to track consistently. And that distinction matters. A missile does not just need to detect a fighter once. It needs a stable target solution accurate enough to guide the weapon through the final seconds of an engagement. If the radar keeps losing the track, The missile may be chasing a position that no longer exists, but the aircraft must also power the system, control the layer, manage the heat, and prevent the electromagnetic field from interfering with its own sensors and communications. A plasma shield is not an invisibility switch. It is a constantly adjusting radar fight wrapped around the aircraft. This is where the F-47 becomes relevant. There is no public proof that the F-47 currently carries a plasma shield, but it represents the type of aircraft that could eventually support a system this demanding. Congressional Research Service data describes the aircraft as having a projected combat radius greater than 1,000 nautical miles and a top speed above Mach 2. From fiscal years 2022 through 2025, approximately $8.2 billion was appropriated for NGAD-related fighter technologies. That shows the scale of the engineering effort behind the next generation of American air dominance. The F-47 is expected to combine long-range, stealth, advanced sensors, electronic warfare, and control of autonomous aircraft. A plasma system would need to connect directly to the aircraft's power system, cooling system, radar, communications, and flight controls. The fighter would not simply hide its shape. It would manage its entire electromagnetic signature as one system. Now comes the problem that could destroy the concept: power. A plasma generator would compete with the aircraft's radar, electronic warfare equipment, communications, computers, weapons systems, and cooling equipment. Suppose, purely as an engineering example, that a future system demanded 1 megawatt continuously. 1 megawatt for 1 hour equals 1 megawatt hour of energy. If most of that energy eventually became waste heat, the aircraft would need to reject approximately 1 megawatt of heat while flying at Mach 2. That is not a small cooling problem, it is a thermal signature problem. The fighter might become harder to detect with radar, but easier to detect with infrared sensors. There is also the aerodynamic issue. A plasma layer can interact with the boundary layer around the aircraft, potentially changing drag, heat transfer, stability, and control behavior. Then comes communications. NASA has studied plasma sheaths around high-speed vehicles because they can block radio communication during atmospheric entry. The same basic effect could become dangerous if a fighter generated its own electromagnetic shell. The plasma could weaken radio links, disrupt satellite navigation, complicate identification systems, and interfere with coordination between the fighter and its uncrewed wingman. The aircraft might need carefully controlled electromagnetic windows, allowing selected signals through while blocking others. The real challenge is not only producing the plasma, it is maintaining the field without blinding the aircraft itself. Even if plasma stealth confused one quantum radar system, it would not make an entire air defense network useless. China could combine multiple radar frequencies, passive sensors, infrared search and track, electro-optical systems, satellites, drones, and electronic emission detection. The radar does not need a perfect picture. It only needs enough information from enough sensors to build a useful track. That changes the contest completely. The real battle is not quantum radar versus plasma stealth. It is uncertainty versus certainty. Now, run the math. The aircraft does not need to remain difficult to track for the entire day. It needs to stay difficult to track during the most dangerous part of the mission. That could mean the final 10 minutes before weapons release, the 60 seconds during an attack run, or the few seconds required to break a missile engagement. A plasma system that works for 10 seconds in a laboratory is interesting. A system that works for 30 minutes at Mach 2 while cooling the airframe and maintaining communications is strategically valuable. The aircraft must survive the full chain: detection, tracking, classification, missile launch, guidance, terminal engagement. If plasma breaks that chain at the tracking stage, the missile may never receive a reliable solution. That is the difference between a scientific demonstration and a weapon. If plasma stealth becomes practical, it will force air defense systems to use more sensors, more frequencies, and more expensive countermeasures. And if quantum radar becomes practical, it will not automatically make stealth obsolete. It will force aircraft designers to control more than shape and coatings. Can an aircraft really turn the atmosphere around itself into a defensive weapon? Or will power, heat, and communication problems expose it first? Comment below. Subscribe for the next breakdown of the weapons changing the physics of warfare. See you in our next videos.